All right, everybody, welcome to the video here for lesson number 1 on Introduction to Sequences. So in today's lesson, we're going to look at kind of just how we develop a sequence. There's a couple of different types of sequences that we'll be dealing with in this chapter, but in lesson 1, we're kind of just identifying, what is the notation that we use for a sequence and just what a sequence really is, kind of like a review of what you did sequence-wise in the beginning of Algebra 1. So the opening exercise asks us to state the pattern and fill in the missing terms. So I'm going to have you pause the video here and see if you can come up with the pattern for us. So if you take a look at this, to get from the first term to the second term, we added 4. To get from the second term to the third term, we also added 4. So if I keep adding 4, I would have 15, 19, 23, 27, and eventually 31. So by adding 4 each time, we've identified our pattern. So we could say our pattern starts at 3, and each term is 4 more than the previous term. So one of the things that we're going to look at a little bit today is just how we can identify what the pattern is. So we'll always state the pattern the same kind of way that we did here in the opening exercise. We'll always talk about what's the starting number and how do we get from that starting number to each number thereafter. All right, and you'll see why once we get to like lesson 4. All right, but for today, we'll kind of keep using that same notation. So how do we define a function? A function is defined where every x value has a unique y value, et cetera, and passes the vertical line test. But when we're talking about a sequence as a function, a sequence as a function has a domain that's just all real whole counting numbers. So decimals are not going to be in this domain. So when we're talking about domain, we're talking about input values. The other thing that we define in a sequence is there's a notation that we use. We use A for our sequence with a subscript of n, right? So this talks about the whole sequence. And then if I do A sub any number, that number tells us the term that we're looking for. So for example, in this particular sequence, A sub n, the first term is 4. So A sub 1 would be 4. Now I have A sub 1, I have A sub 2, I have A sub 3, A sub 4, A sub 5, A sub 6, and A sub 7. I do not have A sub 8, and I do not have A sub 9. So if we look at this pattern kind of quickly, we can get from one term to the next term by doubling the previous term or multiplying by 2. So if I do 256 times 2, I get 512. If I do 512 times 2, the ninth term would be 1024. Then it wants us to divide a bunch of terms here. So if I divide the second term by the first term, I get 2. If I divide the third term by the second term, I also get 2. If I divide the seventh term by the sixth term, I also get 2. So what we're seeing here is if you take any term and you divide it by the previous term, you're going to get the same common ratio of 2. So A sub n, this represents any term. A sub n minus 1 represents the previous term. It's basically saying what we just did here with numbers, but I'm just using variables to talk about any term. So we know that that ratio is going to wind up being 2. So if we wanted to describe this sequence, we'd say it starts at 4, and each term is twice the previous term. You'll see in lesson 3, we'll call this type of sequence a geometric sequence, which you might remember hearing about in Algebra 1. Let's take a look at number 2. Number 2 gives us a sequence of 4, 11, 18, etc. So again, if we look, we have the first term, a sub 1, a sub 2, a sub 3, a sub 4, 5, 6, and 7. What we don't have is a sub 8, and we don't have a sub 9. I'm only going out to 9 because I noticed it asked me to find 9 again here. So to get from one term to the next, I go from 4 to 11. I can multiply by something. I can add by something. I'm adding by 7, though. And if I add by 7 again and again and again, I'll keep getting the next term. So if I do 46 plus 7, I'd get my next term of 53. And then if I add 7 again, I would get our ninth term of 60. So the first term of this sequence is 4, and the ninth term is 60. So if I subtract the second and first term, I would have 11 minus 4. That gives me 7. If I subtract the seventh term and the sixth term, I would also get 7. Right? If you do 46 minus 39, you get 7. Now again, the notation that they're talking about here in this last one is this is any term minus the previous term. It's just a notation. Don't let the a subscript stuff confuse you, right? So if you pick any number for n, say you pick 12, you're talking about the 12th term minus the 11th term. That's what they're asking us to do here. And since we know the pattern already, it's 7. So if I was to describe the sequence, I'd say it starts at 4 and each term is 4 more than, not 4 more, sorry, 7 more. 7 more than the previous term. By using that sentence, I can describe that to anybody and they know what our pattern is, right? Pretend you never even saw the pattern of numbers that's above, and I said, start a sequence at 4 and every term after that 7 more than the previous term. You'd be able to write the sequence 4, 11, 18 just by adding 7 every time. All right. So let's talk about our sequence defined as maybe something that's not a special type of sequence. These first two are special. This one, if you remember from Algebra 1, was called arithmetic. Well, this one's neither. But it is still going to generate a sequence, so we can kind of look at the terms of this sequence. So the sequence is defined by the sentence a sub n equals 2 times n plus 1. So if I wanted to find the first term of this sequence, a sub 1, I would plug in 2 times 1 plus 1. And I would get 3. Now what that means is, on this axis, I have the point 1, 3. If I wanted to find the second term, I would do 2 times 2 plus 1. Notice I'm just plugging in whatever the n value was here for n. This number and this number will always match. So that's going to be 5. So I have 2, 5. A sub 3 would be 2 times 3 plus 1, which would be 7. And you might be saying, I see the pattern. The pattern is, well, what's the fourth term? Right? If I was in class right now, I'd say, all right, so what's the fourth term without having to plug in 4? And you'd all say 9. Because we noticed that it's just adding 2 each time. And there's our sequence. Now, notice it does say to graph the sequence, on the grid between 1 and 5. So here's 1, here's 5. So we've completed the graph between 1 and 5. It's not a line, so we're not going to actually go through and connect the points here. It's a sequence of points that represent this sequence. So we don't want to show anything else other than just those 5 dots. That's all we actually want. Right? So it says, can we connect the dots? The answer here is no. Because sequences only use whole number n values. The reason why is I can't find the 1.5 term of this sequence. I have a first term and I have a second term. I don't have a 1.5 term. So we don't connect the points at all. Now, the next question would also be something that if we were in class, I'd say, all right, so now that you understand the sequence, try and find me the 21st term. So go ahead, pause the video and see if you can come up with the 21st term. There's a couple ways of getting there. All right, so hopefully you got 43. Now here's how we could do it. You could find the 6th term, then the 7th term, then the 8th term, then the 9th term, and keep going forever until you get to the 21st term. Not a terrible way of doing it, just very time consuming. Now, if you were, I don't want to say smart, but if you were conscious of what happened here, this was just a pattern, but it's a linear pattern. So if I was to graph this, right, so if I was to go into y equals and graph 2x plus 1, in my table of values, I would see points like 2, 5 and 3, 7, and eventually 21, 43. That would tell me the value here for the 21st term. Because it was a linear pattern, I can do that. It's a function. So let's take a look at another one. So it says, consider a sequence defined by the pattern such as the first term is 1, and to obtain the next term, you double the previous term. So it tells us the first term is 1, so the second term is double the previous term, so that would be 2. The third term is double the previous term, so that would be 4, right? Double of 2 is 4. The fourth term is double the third term, so that would be 8. And the fifth term would be 16. So let's graph our sequence. You're going to notice this one's going to look a little different. So I have 1, 1. I have 2, 2. I have 3, 4. I have 4, 8. And I have 5, 16. Again, resist the urge to connect those points. We're not connecting points here. We're creating a sequence, so it's just a bunch of points. That's all we're creating. Now, this looks more like an exponential function because it is. It's exponentially changing as we get from one term to the next. So think about how we can find the 10th term of this sequence. So go ahead, pause the video and see if you can come up with the 10th term of the sequence without continuing to double the numbers and double the numbers. You can if you really have to, but see if you come up with a better way of doing it. Go ahead. All right, so if you found the 10th term of the sequence here, right, so if we go into our calculator here and graph 2 to the x power, since I'm doubling every single time. Now, if you look at your sequence of numbers, right, if you look at your table of values, when you have an x value of 5, you actually have a value of 32, which gives you the 6th term. So we can come up with the equation that 2 to the x is not good, right? So we can say here is any term is equal to 2 to the n value minus 1. Now, if you didn't get that in the calculator, don't stress out over it right now. Just keep doubling your numbers how you probably did to get to the answer here of 512. If you got that just by doubling the numbers, good for you. if you understand where this came from, then you're ahead of the game. You're actually already doing what we're eventually going to do, I think, in lesson 3. So you're a little bit ahead of the game here, which is good. All right, so question number 5, if we were in class, I'd say turn to your partner and over the next couple minutes, try and find the pattern for each one of these. See if you can describe what the pattern is. How do we get from one term to the next? Okay, so go ahead, pause your video here and try try these, what is it, 8 of them? Try these 8 and see if you get the same answers as me. I'm going to pause my video as well, and when you come back to the video, you see all the work is shown, so you can see how you did on these. I'm unpausing here for a second so you can check your answers for the first 2. All right, so that first one, I said the first term is 7, and I noticed the pattern is each term is 6 more than the previous, so we could say the next term is 6 more than the previous. For the second one, the first term is 2, and then every term after that is 3 times the previous term. So go ahead, keep going here, see if you get the same answers as me. I'll pause again and then come back with a couple more answers for you. All right, so I did the 2 over here to the right. So I said the first term is 2. The next term is 10 more than the previous term. I notice that I'm adding 10 each time here to get from one term to the next. And then that fourth one was a little bit tricky because the numbers got smaller. So we went from 18 to 9 to 4.5. So we could see that I'm just timesing each one by a half, or dividing by 2 if you said. It's all the same. All right, just seeing that we got from one term to the next here by cutting the previous term in half. All right, so go ahead, try these last 4. All right, so let's take a look. So if you check your answers here, the first 2, they were pretty straightforward. The first one here you saw was 3 less than the previous term, starting at 14. The next one started at -8, and you just added 0.75 each time. Now this one down here was a little bit tricky because of the decimals, right? You might have tried to do addition or subtraction at first, and you notice it didn't work for all the numbers. So then I looked at what I could multiply. Now there's no nice number to multiply here, so I divided the second term by the first term, and I saw that the pattern was multiplied by 0.8. I'm kind of using what we talked about. I'm scrolling back way back to the beginning here in these first 2 questions. So how did I get from one term to the next? I divided the previous term by the term we're on, and I got 2, or I subtracted the 2. That's how we could find our sequences. So I was able to define that one on the bottom left by multiplying the previous term by 0.8. Now, the last one, you might have actually come up with a pattern. There is an actual pattern here. So it starts at 4, I'm adding 5, then I'm adding 10, then I'm adding 20, then I'm adding 40. So I'm doubling the previous value that was added. There's a pattern, but it's definitely difficult for us to define right now. Okay, that's going to be what we call a recursive sequence, which we'll talk about in lesson 4. For right now, just say that there's a pattern there, but we just can't define it using this addition, subtraction, or multiplication kind of idea. So if a sub n represents the nth term of a sequence, how do we represent the term before a sub n? So if a sub n is a term, the previous term is a sub n minus 1. So we're saying the term before n, so we're subtracting 1 from n. I can say the next term, so if I'm at a sub n and I want the next term, I would add 1 to n to get to the next term. For example, if I was at a sub 8, the previous term would be a sub 7, 1 less. The next term would be a sub 9, 1 more. That's how we would do this. Now that's the lesson. The homework is going to be included here in this same video, so I would pause here for a few minutes or come back to the video. Try the homework first, right? Don't just watch this as one continuous video, okay? So pause or come back to it. Try the homework questions first and then come back and see if you got the right answers to the homework. All right, so welcome back. Hopefully you tried your homework on your own and you're just checking answers at this point. So number 1 in the homework assignment gives us this sequence. We go from 4 to -1 to -6 to -11. So we could see that each time we're going down by 5. Right, so if we want to describe this sequence, we would say it starts at 4, and the next term is 5 less than the previous term. The third term of the sequence was -6. The fifth term we'd have to find, so we have the fourth term. So the fifth term here, we would subtract 5 again, we'd be at -16. If we subtract the first term and the first term, we would have -1 minus 4, which gives us -5. And if we were to subtract the fifth term minus the fourth term, we would also get -5. Just watch your signs there. Number 2 says sequences do not always need to have an additive or multiplicative pattern. Consider the following sequence A sub n: 2, 4, 6, 8, 0, 2, 4, 6, 8, 0, 2, 4, ... So what is the fifth term? So we have the first, second, third, fourth, fifth term. So this would be A sub 5. That's 0. If I kept going here, I have 5, 6, 7, 8, 9, 10, 11, 12. This is the 12th term. So if I wanted to find the next term of the sequence, the 13th term here, we would look at my pattern and say after 4 I got 6. Then comes the big question. Can we find the 2018th term of this sequence? So since this sequence comes in sets of 5, right? Every single set of 5, the sequence repeats itself. At A sub 2015, which would be a multiple of 5, right? Where would I be, right? I would be back at 2. So if I want to find 2018th term, it would be 3 more than 2. So here's 2015. This would be 2016. This would be 2017. This would be 2018. That's the term we want, is 8. 2019 would be 0. And then 2 would be at 2020, which would be another multiple of 5. That's how we would do that question. We're just seeing what the sequence is telling us. Let's take a look at number 3. Number 3 gives us a sequence here shown by little boxes or tiles, whatever you want to say, squares. So it says the first term of the sequence, so this would be A sub 1, is 16. The second term of the sequence, A sub 2, has 2 less boxes, so that would be 14. The third term of the sequence has 4 less boxes than the original, so that would be 12. A sub 4, this has 10. And A sub 5 has 8. So we can see each time the number of boxes is going down by 2. So it says Rosie proposes the explicit sequence definition. Explicit means that you can just plug in the value and you get the actual sequence number. Because she notices that there are 16 squares initially and each subsequent pattern has 2 less squares. Does this sequence make sense? So if we were to plug in A sub 1, I would have 16 minus 2 times 1, which would give us 14. That doesn't work because the first term of the sequence should be 16. Now, it's going to eventually generate a pattern similar to this one. I'm not at the right starting number. So what we could talk about is how we could actually figure out how we could change Rosie's explicit formula so that it would work for this sequence. So to change her formula to make it work, I can say A sub n is equal to 16 minus 2 times something. Now, the problem that we had with plugging in 1 is we actually subtracted 2. I want to subtract nothing, so I'd say n minus 1. By making that one little change to this pattern, if I plug in 1, I get 16 minus 2 times 1 minus 1, which gives us 16. If I plug in 2, I'd say 16 minus 2 times 2 minus 1, which gives us 14, and we would actually generate the pattern correctly. So Rosie's explicit sequence definition is actually incorrect. That's what we're going to spend a ton of time on here in lesson 2, right? If you got that right now, awesome. If you just noticed that her equation did not generate the pattern, good for you. That's all we really needed to get out of number 3. Hopefully this video helped, and hopefully I see you soon.